discussions so far about distillation curves and distilling point have treated the shape of the curves and temperatures close to 900 degrees Fahrenheit somewhat vaguely, but on purpose. There is a phenomenon that happens at these temperatures called cracking. Refiners use cracking extensively, but in controlled ways. In the distillation process, all the uncontrolled symptoms of cracking can occur. To avoid them, refiners developed vacuum flashing. Subject: the cracking phenomenon. Suppose a technician going to develop a crude distillation curve blend. Technicians do that all the time to prepare note essays for use by refiners to develop and assess the strength of the crude. The technician note record the temperature, capture the phase and record and accumulate the following molecules. If the technician permits the temperature of the molecule to rise to about 900 degrees Fahrenheit, a sudden change in the shape of the distillation curve will take place. As the temperature went from 900 to 1,000 degrees Fahrenheit, the cumulative volume recovered would exceed 100%, and crude would still be boiling in the pot. This might exaggerate what anyone can easily observe with the naked eye, but it makes the point. As the complicated hydrocarbon molecules, they have not yet vaporized at 900 degrees Fahrenheit, are heated to higher temperatures, the energy transferred from the heat is enough to cause the molecules to crack into two or more smaller molecules. For example, in figure 4.1, a molecule of carbon-16 hydrogen-34 may crack into three pieces: carbon-8 hydrogen-18, carbon-6 hydrogen-12, and carbon-2 hydrogen-4. A fuller discussion of the chemical reaction of cracking will be covered in the chapter on cat cracking. If you recall the discussion on boiling points, it starts to become apparent why the shape of the distillation curve behaves so strangely at this point. The smaller molecules boil at much lower temperature than the larger ones. As cracking creates them, they leap out of the crude oil. That tells only half the story. Why does more volume get created so that the distillation curve exceeds 100%? In simple terms, the smaller molecules take up more room than the larger ones. Again, recall the discussion on hydrocarbon properties and specific gravities. The compound C16H34 weighs 7.2 pounds per gallon, and C8H18C6H12 and C2H4 weigh 5.9, 5.6, and 3.1 respectively. Take a gallon of C16H34 and suppose you could crack it completely into these three compounds. It never happens that way. Combinations of different compounds turn up too. The chemistry of it says that there would be 50% C6H18, 30% C6H12, and 12% C2H4. The percentages are by weight, not by volume. Figure 4.2. To make the calculation easy, start with 7.2 pounds of C6H34 and calculate the change as follows. Note the calculations on the top of page 41. Cracking is a lucrative process only when it is controlled. The distilling unit is not designed to control it, so refiners avoid it by not raising the temperatures in the distilling process. The heaviest cut point on the distilling column is around 750 degrees Fahrenheit. There are, nonetheless, lots of hydrocarbons that need to be separated from the straight-run residue, and the technique used is vacuum flashing. Subject: effects of low pressure. Suppose you own a chain of restaurants that specialize in serving stuffed baked potatoes, one in Houston, Texas, and one in Denver, Colorado. Do you know that baking potatoes in Denver takes 20 minutes longer than it used to? I found that out the hard way when I went skiing in the Rocky Mountains and cooked my own supper at night. The reason is that at the higher altitude of Denver, the atmospheric pressure is lower.